right? And we had looked at how we have an issue with these two compounds having the same name. Okay? They would both be called iron oxide, which is problematic because they're different compounds, they have different chemical and physical properties, they can't be substituted for each other. Okay? That's an issue. So what we have to do is we have to communicate to people which iron we're dealing with, because iron is a multivalent metal, meaning its electron distribution or structure can be different depending on what kind of iron you have. Sometimes certain orbitals are more full than others. Okay, so iron can have either a 3+ charge or a 2+ charge. Now, the problem comes in not so much that part of it, that's easy to remember. The problem is figuring out which charge is involved. Okay, I can't just look at this formula and say, well, it must be this iron. I have to actually figure it out. Okay, everyone follow me there? And I think we kind of got to that point yesterday. That's kind of where we left off. All right, so if I'm looking at this compound here, I know that iron has 2 possibilities for a charge, but how many possibilities are there for oxygen? Only 1. So you always look to the non-metal to help you out in this situation. Oxygen's always -2. How many oxygens are there? 1. Okay, which means there's 2 negative charges in this compound. All compounds have to have a total charge of 0. Okay, so that means this iron has to have a +2 charge, and now we can write that this is iron, Roman numeral 2, oxide. Okay, and we do the same thing here, okay, with this one, except now obviously we got more numbers to deal with. All right, so oxygen is still always a -2, but now how many are there? 3. Okay, how many negative charges in total here? 6. -2 times 3 is -6. So I need to get 6 positive charges out of 2 irons. Everyone follow my reasoning there? Okay, so I just take whatever I got to get and divide it by how many I have to get it from. So 6 over 2, this is the iron with the 3+ charge, and this is iron, Roman numeral 3, oxide. All right, does that make sense to everybody? Okay. So you have to work backwards a little bit on those. Okay. Remember, don't just reverse the swap and drop. I know on this compound that works. All right. But on other compounds it may not, because sometimes we get a compound that when we drop and swap is like this. The first one's a 2 and the second one's a 4, but we don't leave it that way. We always reduce ionic compounds. Right. So we would end up with this A, B2, and if I just reverse the swap and drop, it would tell me this is a 2+ charge when it should actually be 4. Okay, so it would work like about 2/3 of the time, right? And I kind of like being right more often than that. Okay. All right, I want you guys to try these ones. Obviously, you don't have to do number 1 because that was the example that we just did. Okay, so I want you guys to write the names of these. They are all going to require Roman numerals. Okay, so you'll need your periodic tables. Okay, and looking those up. Let's say do the first, do up to number 5, and then I'll go over them. So I'll give you a couple minutes, then we'll go over the first 5. All right, so for number 2, we've got cobalt and sulfur together. Okay, cobalt is right here. Okay, its possible charges are 2 and 3. Okay, if I look at sulfur, sulfur is always -2, so this has to be cobalt 2. All right, so this stuff would be cobalt, Roman numeral 2, okay, sulfide. All right, for number 3, I've got manganese, Mn, and chlorine, right? Manganese can have a 4+ and I think a 2+ charge, something like that. In the end, it doesn't really matter what its possible charges are. I can figure out what its actual charge is just by looking here. Chlorine is always a -1, and there are 4 of them. Okay, that means I have a total of 4 negative charges, so I've got to get 4 positives from the only single manganese atom there. So this has to be manganese 4 chloride. Okay, and then we've got copper with sulfur. Okay, copper can be a 1 or a 2. Okay, in this case, it must be copper 2. Okay, and then for number 5, okay, I've got tin and tellurium together. And tellurium is, I think, always a -2. Is that right? Okay, so tellurium's a -2, and there are 2 of them, which gives me in total 4 negative charges. So the charge on tin, since there's only 1 of them, has to be 4. All right, so we're looking at tin, 4, telluride. Okay, how many people are done past 5? I told you to stop at 5. Okay, keep going. Give you a couple more minutes and we'll do up to 10. All right, so for number 6, I've got mercury with astatine. Okay, astatine is always a -1. Okay, so that gives me a total of 2 negative charges. So this must be the mercury with the 2+ charge. So this is mercury 2 astatide. Okay, and then for number 7, we have polonium with iodine, and iodine's always a -1 as well. So that gives me a total of 4 negative charges, which means polonium has to have a charge of +4 because there's only 1 polonium atom. Okay, and then number 8, we have antimony and sulfur. Okay, and antimony is a weird one. It's a metalloid, actually. And it can be a 3 or a 5. Okay, and it can be actually plus or -3. It's really weird. So we look at sulfur. Okay, sulfur is always a -2. Well, -2 times 3 is -6. So I've got 6 negative charges there. Okay, and I've got to get 6 negatives out of 2 antimony. So +6 divided by 2 is +3. So this is antimony, Roman numeral 3, sulfide. Okay, and then for number 9, I've got nickel and nitrogen. Nitrogen is always a -3. -3 times 2 is -6. That means I've got to get 6 positives out of nickel. 6 divided by 3 tells me that nickel has a 2+ charge. All right, and then our last one, we have ruthenium with oxygen. Oxygen's always a -2, so there are 4 negative charges here, and ruthenium must then, since there's only 1 of it, have a +4 charge. Okay, questions on those? All right, the place where people mess these up is not in that they can't figure out the Roman numerals. That part's pretty straightforward. It's that they forget some of these need Roman numerals, or that they over-apply the Roman numerals and they started using Roman numerals on compounds that don't require them. Okay, so the thing you need to remember is you only use Roman numerals if something has more than 1 possible charge. Okay, so basically the transition metals, many of them here through the middle. Okay, everybody follow me there? All right, that becomes a bit more of an issue for people when you get really good and you're starting to remember all the symbols and you don't look at the periodic table as much to get them. That's when you forget usually to use the Roman numerals. Okay, you just forget that chromium's got more than 1 charge because you know that it's Cr and you just write it down. Right, so always make sure you check if you've got a metal in the middle. Okay, check that it needs Roman numerals or doesn't need Roman numerals. All right, any other questions there? Okay. Now, next thing here, before we move on to the molecular elements. On the top part of your periodic table, you will see a table of common polyatomic ions. Okay, what a polyatomic ion is almost kind of like a failed compound. Okay, because a true compound has a charge of what? 0. However, these are groups of atoms that are stuck together that do have a charge. So they are not a true compound, okay? They are an ion because they are a charged particle, right? They go into ionic compounds in exactly the same way that nonmetals or metals do, okay? The only trick here is that naming and writing the formulas becomes a little bit trickier, okay? So let's say I'm looking at that compound there. As soon as I see that there's more than 3 elements in this compound, I know it's not a binary ionic compound. right? I'm not going to go, that's potassium oxygen hydride, because that's not how we name it. Okay? As soon as you see that you've got a metal and there's more than 2 elements in a compound, you've got to go to that table at the top. And you've got to look up that other thing. Okay? So on there should be OH somewhere. Hydroxide, right? OH is hydroxide, right? So this stuff is potassium hydroxide. Okay? We don't change the name of the polyatomic ion, right? So in that way, actually naming them is a little easier. You don't even have to think. You just need to write it down as it appears in there. Okay? The trick is just recognizing that you have to find it. So this stuff would be potassium, well, PO, potassium hydroxide. See, I almost did it myself. Okay, potassium hydroxide. This stuff is a really strong base, actually. What about, let's say, this stuff? I think that has a +2 charge. Oh, you got your hand up? Okay. Okay, so the ion here is hydrogen carbonate. So this compound would be calcium hydrogen carbonate. Okay, all we have to do is write down the name as it appears in there. Why did I put brackets around this? Exactly. It's just like in math. You put brackets around something if you want to put a number outside that applies to the whole thing. Okay? This 2 says that there are 2 hydrogen carbonate ions in this compound. And I get that because if I was doing the drop and swap here, okay, you can see on your chart there that hydrogen carbonate has a -1 charge, kind of like chlorine or iodine or any of those. Okay? And calcium is a 2+. So when I drop and swap, the 1 goes here, but we don't write 1s, and the 2 goes over here. Okay? But as Peter was saying, if I leave it like that, that doesn't say there's 2 hydrogen carbonate ions. It says there's 1 hydrogen atom, 1 carbon atom, and 32 oxygens, which isn't right. Okay? You guys follow the difference there? Okay? So once in a while, for these types of ions, we have to use brackets when we write the formulas. Okay? You don't use brackets for anything else, only for polyatomic ions, and only if you need it. Okay? If this ended up not needing a number out here, I wouldn't need the brackets either. Okay? Everybody follow there? We'll work on a few more of those in a minute. I just wanted to show you those are ionic compounds as well. The rules for naming, it's still metal first, and this is acting as a nonmetal. How do I know it's acting as a nonmetal? Well, actually, there's one on there that acts as a metal. It has a negative charge. All the nonmetals are negatives. All the metals are positives. Okay? You have one polyatomic ion in the chart that is acting as a metal with a positive charge, and that's ammonium. It's one of the first ones, the second one. Okay? NH4. It's the only positively charged one in there. All right? Everybody follow there? Okay. All right. Molecular compounds. So you have a molecular compound when you have 2 nonmetals reacting to form a new substance. With a molecular compound, you have now 2 atoms going together that both need electrons. So if they both need it, it's not like they have any to give away. It's not like when an ionic compound forms where, you know, the metals got ones it can afford to give away and the nonmetals can take them. Okay? Now it's, well, neither of us has enough. Now we're going to have to share. Okay? So in a molecular compound, the bond is actually way stronger because they both need each other all the time. Okay? They can't give anything away, and they both have something the other needs, so they have to stick together. All right? So these bonds are incredibly strong. The prime example is water. Okay? So here's a water molecule. This is the oxygen atom here. Okay? These are the 2 hydrogen atoms. Hydrogen has 1 proton, okay, and 1 electron. Oxygen has 8, okay, so it has 8 protons and it has 8 electrons. If it wants its outer shell to be full, it needs 2 more. Okay, it needs 12. All right. So what we want here is for, sorry, it needs 10. Sorry, not 12, 10. Okay, it needs 10 electrons. So what it does is it bonds with hydrogen and with this hydrogen. Okay, now hydrogen gets a full outer shell and oxygen gets a full outer shell, but they have to stay together in order for that to be true. Right? So they are going to share these electrons. That gives oxygen 8 electrons in the outer shell, hydrogen 2, okay? But if they split off, now they don't have full outer shells and they're no longer happy. Okay? So in order to stay happy, they got to stay together. Okay? Everybody follow me there? Now, that means though that there's no charged particles going to be formed here because these guys aren't going to split. Okay, so there's no charge balancing that goes on, there's no exchange of electrons, and there's no splitting up, which means generally molecular compounds are less soluble in water. Okay? Ionic compounds, they're usually really soluble in water. Right? They dissolve easily and they split. Okay? These things are usually less soluble. That's not saying there aren't molecular compounds that aren't soluble in water. Sugar's a molecular compound, it's highly soluble in water. Okay? But lots of other ones are not, like butter and oil, okay, and things like that. Those are organic molecular compounds and they don't split, okay? So they don't dissolve very well. Everybody follow my logic there? Okay. So we call this a molecular or covalent bond because valence is the outer shell and they're sharing it. So covalent, they're sharing an outer shell. All right, when we name molecular compounds, we don't have a metal, so we can't just say always name the metal first. You got 2 non-metals here. So when you're naming a compound, you just name it in the order it's written. If nitrogen comes first, you name nitrogen first. Okay? If hydrogen comes second, you name hydrogen second. Okay? Whatever it happens to be, that's the order that you go in. Right? The problem is that when nitrogen and hydrogen go together, there could be a number of different ways they could do that because, again, they're not trading electrons. All right, so there's no fixed ratio for them to go together. It's still going to be a whole number ratio, but it's not fixed. It could be 2 to 1, 3 to 1, 4 to 1, who knows? That's why we have to use prefixes for molecular compounds. Right? We have to actually tell people in the name, here's how many of each atom there are, because there's possibilities of any number of combinations. Okay? Possibilities, not all likely, okay? But there's other possibilities. All right, so they arise when 2 or more nonmetals react to form a new substance. Okay, the electrons are shared. Okay, so molecular compounds, electrons are shared rather than gained or lost. Okay, and these compounds are very stable. Okay, the difference between naming ionic compounds and molecular compounds is that in molecular compounds, we use prefixes to denote the number of atoms. All right, so some examples. Okay, this stuff here is carbon disulfide. Right, di stands for 2. Okay, and this stuff here, this name is actually wrong. What am I missing? I'm missing mono in front of the oxide. Okay, this stuff should be dinitrogen because there's 2 nitrogens. Monooxide or monoxide, we usually abbreviate it. So that's actually wrong. It should be monoxide. So I put a mono in front of that one. Why didn't I put a mono in front of this one? Right. You never put mono on the first one. Okay? I don't know what chemists have to be difficult. Okay? They just got to have special rules that make them feel important, I guess. Okay? For some reason, you never put mono on the first thing. Right? But you put any other one that is required other than that. Right? So carbon disulfide, dinitrogen monoxide. Okay? This one here, okay, tetraphosphorus pentaoxide. Okay, sorry, decaoxide, pentaoxide, decaoxide. All right, prefixes. How many people know the prefixes to 10? Okay, well, we'll write them down just to be safe. Okay, all right, so 1 is mono, 2 is di, 3 is tri, okay, 4 is tetra, and after that, they're just like the shapes, okay? 5 is penta, Okay, 6 is hexa, 7 is hepta. Do not write septa. Mr. Real, the chemistry guru, hates that. Okay, just I don't know why, just rubs them the wrong way. Okay, so don't write septa if you're going into Mr. Real's class. Hepta. Okay, and then 8 is octa, 9 is nona, and 10 is deca. And you probably won't need anything above 10.
Would you also be bi?
Not for naming compounds, no. Yeah. So that's a good question. No, you should not write it as something bi-oxide. It's dioxide. Okay. In chemistry, they always use di instead of bi. Okay, with molecular compounds, like we said, the electrons are shared. Now, this sharing can also happen with some elements on the periodic table. Some elements are what we call molecular elements. That is, they bond and form molecules with themselves. Okay, you should probably take out your periodic table here. I photocopied your periodic table in black and white. There is a color version of it, and you can kind of see that because I have a legend up here at the top, but it's kind of hard to tell the different shades of gray, okay? But I've tried to identify the different molecular elements. So just so you might want to mark them, or if you got a highlighter or something like that, you might want to do this, okay? The molecular elements, that is the ones that come in pairs, so always as a 2, right, are nitrogen, oxygen, and everything in group 17. Can't remember if I have the periodic table on here. I thought I did. Guess not. Okay, you also need to mark hydrogen. That's hydrogen is also a molecular element that pairs with itself. I mean, that one's kind of obvious. If it pairs with itself, both hydrogen atoms would have a full outer shell with 2 electrons in it. Okay. Okay, now, the thing to remember here is that those only come as 2s when they are by themselves, not in a compound. Okay, if oxygen is in a compound, it could be any number. It could be 1, it could be 2, it could be 5. Okay, it can be any number. It's only when oxygen is by itself. If oxygen is written as an element, it is O2. Same with nitrogen, same with chlorine, all of those. Okay, then you have a couple of special ones. Phosphorus is also a molecular element, but it comes in sets of 4. Okay, or tetrads. Okay, so whenever phosphorus is by itself, it's written as P4 when it's by itself. In a compound, again, it could have any number, right? But when it's by itself, it comes in sets of 4. Okay, and sulfur comes in octets. That is, when sulfur is by itself, it will bond with itself 8 times. S8. Right? Those are your molecular elements. For right now, knowing that is less important, but as soon as we start writing chemical reactions, if a reaction says sodium chloride reacts with sulfur, you need to know that sulfur is S8 when you write the reaction out, or it doesn't work. Okay? All right, so if you've got those marked, that's good because you're going to need those marked. All right, so when we write molecular compounds, we've got to have prefixes on them. Remember, we don't put mono on the first one. That's basically what you need to remember. All right, try the first 5 here. Okay, write out the names with the prefixes. Okay, and then we'll go over the first 5 and we'll see where we're at then. Okay, we're going to run out of time here because I forgot it's short class Friday. Okay, so with this one here, we've got nitrogen and iodine. So this is going to be nitrogen triiodide. Okay, and this stuff here, we got carbon and iodine. That's going to be tetraiodide, right? So carbon tetraiodide. Now, guys, some people ask, should I hyphenate that? Probably. I'm not an English teacher. If you don't hyphenate it and it's still carbon tetraiodide, I'll mark it right because that's what the name is. I don't know punctuation. Okay. Yeah. All right. Number 3, got nitrogen, but there's 2 of them and 3 oxygens. So this stuff is going to be dinitrogen trioxide. All right. Have a good long weekend, but not too good.